finally we get to put it all together. We're actually going to evaluate, meaning we're going to find the exact value of a definite integral using infinite limits. All right, so we're going to use an approximation method with an arbitrary number of rectangles. We're going to let that arbitrary number of rectangles approach infinity, and we're going to see what happens. We've done an example already with this integral. We've been approximating this integral in one way or another for a little while now. So we're finally going to evaluate it. We're going to say that the integral from 1 to 3 of x squared with respect to x is equal to the limit as n approaches infinity of the approximation we get with n rectangles with our right rectangular approximation method. And so that is going to be equal to the limit as n approaches infinity of that expression that we got earlier, 26n squared plus 24n plus 4 over 3n squared. We already did the work for that. We don't have to do it again. Okay, so we said that this is the approximation for any number of rectangles where the number of rectangles is n. Well, this is actually a really easy limit to evaluate. This step is one of the easiest steps in this whole process of solving the area problem. We have a limit with the degree on top, or a rational function where the degree on top is the same as the degree on the bottom. So what's the trick? Divide those leading coefficients. So this is going to equal 26 over 3. And we're done. Do we not like decimals? We hate decimals, unless it's a calculator test. But this, at no point in this problem did we need to use a calculator, which tells me this is the type of problem you would see on a non-calculator test. So check it real quick. Or you can just check back in your notes. 26 over 3 is 8 2/3. So 8.667 would be the approximation to the nearest thousandth. Is that what we got when we evaluated this integral with the calculator? Yeah. So not only did we evaluate it by hand without a calculator, but we got a more exact answer than the calculator did. The calculator had to round it to like 15 decimal places. We didn't have to round. We've got it to thirds. Or we've got an exact answer as a fraction. Now, that being said, we knew that it was 8 2/3 looking at it. But the calculator doesn't know that. It just approximates it using a decimal. This is limited. I said this earlier. This is a very limited process. And the reason it's limited is because the type of function that we can do this with our sigma notation, with this, is very limited. If you look at the sigma formulas I gave you, we have a sum formula for a constant. We have a sum formula for I. We have a sum formula for I squared, and we have a sum formula for I to the third power. There are formulas for higher degrees of I, but they get more and more complicated. So if we wanted to do this for a polynomial of degree greater than 3, say a 4th degree or 5th degree, we would need those higher formulas, and we would be dealing with things that are more complicated. If we wanted to do something like this for, say, e to the x, or sine, or cosine, or tangent, we can't do it. Those sum formulas all of a sudden don't do anything for us. We can't find the sum. Let's say f of x was sine of x. We can't just simplify the sine of 1 plus 2 over n and add a bunch of those together using some simple formula like we did with the other ones. Now I know you may be thinking, okay, those formulas aren't really that simple. They're simple relative to what we would have to do with sine or cosine or tangent. So the area problem is a problem that was able to be solved using fairly simple algebra. Okay, nothing we did here was actually calculus, with the exception of the idea of the limit. So it didn't take until this last step here to actually to use a calculus idea. But we can't do it with things that aren't polynomials, and we can't do it with big polynomials. So we're going to have to come up with ways of evaluating that definite integral that don't involve these Riemann sums. Remember, the Riemann sums are the approximation methods, okay, using rectangles or trapezoids.